In Chapter 5.1, we're going to be doing an introduction to trigonometry and going over angles and radian measure. So to get started with a couple definitions here, the definition of an angle is going to be the amount of rotation from an initial ray to a terminal ray. So we have these two arrows right here. Those are our rays. So this first one is the initial ray, and the second one is the terminal ray. And the point at which they meet is called the vertex. So an angle, it starts at the initial ray and it opens up to the terminal ray. So it would look something like this. And we tend to denote angles with the Greek letter theta. So let's write out some of the other angles that we can use. So we have theta, we have alpha, and beta, or phi/phi, depending on how you pronounce it. So those are kind of the four main ones that I'll probably be using throughout this section and going forward. So usually when we're drawing angles, we draw them in what's called standard position. So an angle is in standard position if the vertex is at the origin and the initial ray lies along the positive x-axis. So for an example of what this would look like for this one on the left here. So the initial ray is on the positive x-axis and it would be opening up to some terminal ray. So the angle would look like this. And another way that we can see it is if the angle, so initial ray on the positive x-axis, and if it's turning the other way or rotating the other way, it could look like that. So the one on the left is going to be a positive angle. So theta is positive. Positive angles are when they're generated counterclockwise from initial to terminal ray. And the one on the right would be a negative angle because it's generated clockwise from initial ray to terminal ray. So there can be positive angles and negative angles. So there's going to be two types of ways that we can measure angles. It's going to be degrees and or radians. So starting with degrees here. So when we're measuring with degrees, we have to make sure that we're using the degree symbol, the degree notation. And it's important to remember that there's actually no lower or upper bound for angles. It can be any real number. So something can be 1,000,000 degrees. It can be negative 10 billion degrees. There's no lower or upper bound for angles. So I just put down a couple of important angles. So the first one is an acute angle. An acute angle is any angle between 0 and 90 degrees. So that would look something like this. Something opening up in the first quadrant. The next one is a right angle. That's going to be theta equals 90 degrees. So that would be a right angle. So if it's a right angle, we can put a little square angle to represent theta. Next, for an obtuse angle is going to be between 90 degrees and 180 degrees. So that's going to be in the third quadrant. Or sorry, not the third quadrant, the second quadrant. And for the last couple here, a straight angle is going to be exactly what it sounds like, which means it's going to be 180 degrees. So it'll look like this. And for the next one, for 3/4 of a rotation, so this one doesn't really have its own name like the other ones had a name. 3/4 of a rotation is going to be 270 degrees. So that's going to be 3/4 of the way back to its starting point. So it'll look like this. And the next one, a full rotation, is going to be all the way around. So the initial ray and the terminal ray are going to be right on top of each other. That full rotation is 360 degrees. Okay, so those are some important ones for measuring in degrees. I'm sure for the most part that's what we're familiar with. The next way is we can measure angles in radians. So radians actually don't have any units. If you wanted to have a unit, you would just call it radians. So the definition of 1 radian is going to be the measure of the central angle. So we're going to be working with a circle here. It's going to be measure of the angle when the intercepting arc between the two rays is equal to the radius. So it might not make too much sense yet. So let's say we have this circle and we have the initial ray right here. And let's say we have this terminal ray right here in such a way that this radius of the circle is going to equal the length of the intercepting arcs from those rays. When that is the case, then this angle right here that is formed equals 1 radian. So essentially a radian uses the radius of a circle to help us figure out the definition of the angle, hence the name radian. So for radian measure, degrees in radians, let's draw a diagram so we see what these units represent. So let's say we have a initial ray and a terminal ray. And let's say the radius is r. And this arc length, so from where the initial ray and the terminal ray both intersect that circle, we're going to call that s. And then, of course, this is our theta. So theta is going to equal s, which is the arc length, divided by r, which is the radius of the circle. So that is the definition of radian measure. So let's do an example using this definition. So let's say a central angle theta in a circle of radius 6 inches intercepts an arc of length 15 inches. We want the measure of theta. Okay, so let's draw these rays in here. So we have a radius of 6 inches. And we have this intercepting arc of 15, and this is our theta. So we know that theta, based on that definition from above, equals s over r, which is going to be theta equals 15, the arc length over the radius, which is going to equal 2.5. So you can just leave it like that, or you can call it 2.5 radians. So if you leave off units, it's implied that it is in radians. Okay, so we can actually convert between the two, between radians and degrees. So what we can do, we can use that definition from the previous page, theta equals s over r. And let's say we want the arc length to be the whole entire circle. If the arc length is, meaning the circumference, if the arc length is the whole entire circumference of the circumference of a circle is 2 pi r. So if we simplify that, 2 pi r divided by the radius of a circle, the r's actually cancel each other off. R divided by r equals 1, and we're left with 2 pi. So the significance of this is that this is the same as 360 degrees. So what that means is 360 degrees equals 2 pi radians. So one full rotation around a circle is 2 pi radians. So what that means is we know 360 degrees equals 2 pi radians. We can simplify that by dividing both sides by 2. And that means 180 degrees equals pi radians. Okay, so that's something that we should have memorized. So we're going to be converting between the two. So if we're converting degrees into radians, essentially what this is just going to be a proportion that gets set up. But the quick way to do it is to multiply the degrees by pi radians over 180 degrees. That'll cancel the degrees, and then we're just going to be left with the radians. And if we're converting from radians to degrees, we multiply the radians by 180 degrees over pi radians. That'll cancel the radians and we'll be left with degrees. So it's the same conversion, we just, one of them, they're just the reciprocals of each other. Okay, and I put a little note here. Most of the time, we're going to have radians as a fraction in terms of pi. So we're going to want to simplify the fraction, but keep pi as pi. So here is another way to think about it, just kind of using a circle, a visual representation. So let's go back to what it means to be 1 radian. So if this is the radius of a circle, and let's say we go 1 radian, so that means that this is also length r if that angle that opened up is 1 radian. So let's do that again. Let's say we go another radian. So the total angle from here to here would now be 2 radians. Let's do another one. That would be another radian. So far we have a total of 3 radians, an angle of 3 radians from that initial ray to that final terminal ray. So if we go one more time, not one more full time, but if we want to get a straight angle, it would look something like that. So that little portion right here is not 1 full radian. It's actually going to be about 0.1415-ish radians. So what that means is it takes actually pi radians, it's 3.1415-ish radians, to go halfway around a circle. So that means it goes pi radians around the circle, which is 180 degrees. So pi radians equals 180 degrees. So if we wanted to go around another half of a circle, that would be another pi radians, which would make it 2 pi radians for the full rotation around the circle. Okay, so let's do a couple examples. I won't do all of them because I put a lot on here just to make sure we're good with them. So let's convert from degrees to radians. So the first one is 30 degrees. So multiplying 30 degrees by the correct conversion, we have to multiply by pi radians over 180 degrees. So when we multiply this, it's going to be 30 divided by 180. 30 divided by 180 is 1/6. So that's going to be 1/6 times pi. Typically, you're not going to want to write it like that. You're going to want to write it as pi over 6. So 30 degrees equals pi over 6 radians. So notice that the degrees cancel, degrees over degrees, units cancel. So next for 90 degrees, 90 degrees times pi radians over 180 degrees. So that's going to be 90 divided by 180, which is 1/2. So that's 1/2, the degrees cancel. That's 1/2 times pi, which is pi over 2 radians. Okay, and then for the next one, it's negative 135 degrees times pi over 180 degrees. So I'm going to leave out the word radians now, just because, like I mentioned, we actually don't need to write it. So negative 135 over 180. So remember, you don't want to write it, you can write it as a decimal technically, but get in the habit of writing it as a simplified fraction instead. So this is going to end up being negative 3 pi over 4. So negative 135 over 180 simplifies to negative 3 pi over 4 radians. Okay, so hopefully we got a hang of that. I'm just going to fill in the rest of these real quick. Okay, so here are the last couple. So 45 degrees equals pi over 4 radians, 270 degrees equals 3 pi over 2 radians, and negative 540 degrees equals negative 3 pi radians. Okay, let's do a couple examples converting from radians to degrees now. So convert pi over 3 radians into degrees. So we're going to start with pi over 3. I'm not going to write radians. So now the conversion rate is we multiply by 180 degrees over pi radians. So when we do this, you'll notice that the pi's actually cancel. So pi over pi is 1. So it's 180 degrees divided by 3, which is 60 degrees. Okay, next one, negative 5 pi over 3 radians. I'll just do 2 more and then I'll pause it and do the other ones. So negative 5 pi over 3. And to convert, we multiply by 180 degrees over pi. So pi over pi cancels to 1. Negative 5 over 3 times 180. We end up getting negative 300 degrees. Next one, we have 1 radian. So this one looks a lot different, right? It's just 1 radian. All the other ones were in terms of pi. But we're going to do this the same way. We're going to multiply 1 times 180 degrees over pi, which is just 180 degrees divided by pi. And we're going to have to round for this one. It's about 57.3 degrees. So 1 radian, which hopefully we remember why it was kind of important from a few pages ago, 1 radian is actually equal to 57.3 degrees, which seems like a pretty insignificant number when we write it in degrees. Okay, and now for the last 3, I'm just going to pause it and fill these in. So for D, pi over 4 radians equals 45 degrees. For E, pi over 8 radians equals 22.5 degrees. And for F, we have negative 5 pi over 8 radians equals negative 112.5 degrees. Okay, let's do a few examples that look similar to ones that we've already done before, but we'll see that there's a little bit of a difference. So let's say we have a circle with radius 10 inches, and we want to find the length of the arc intercepted by a central angle of 120 degrees. So let's draw this out. So we know the radius is 10 inches, and we know this angle is going to be 120 degrees, and we know that this arc is, we're looking for the arc, so I'm going to call it S. Okay, so we have this formula, theta equals S over R. We're looking for the arc length this time, we're looking for S. So to solve this for S, we would have to multiply both sides by R, and we would get S equals R times theta. Okay, we also have a little bit of an issue here. We need theta to be in radians in order to use this formula. So theta in radians, we have to convert 120 degrees to radians by multiplying by pi over 180. It ends up simplifying to 2 pi over 3 radians. So that is our theta. So now we can solve for S. S is going to equal 10 times 2 pi over 3. So solving this, we get 20 pi over 3. So we want this as a decimal answer because 20 pi over 3, we want it as an actual length. So we're going to have to round it a little bit. Plugging this in the calculator, we get 20.94, and the units were in inches. So that would be the length of the arc length. Okay, and then for the next one, let's say we have a circle has a radius of 20 centimeters. We want to find the length of the arc intercepted by a central angle of 270 degrees. So here's the radius of 20. A central angle of 270, that was 3/4 of a rotation. So we're looking for this big arc length from the initial to the terminal ray. So once again, we know that theta equals S over R. We are looking for the arc, so we solve it for S again. We get S equals R theta. And we need theta in radians. So we're going to convert 270 degrees to radians by multiplying by pi over 180 degrees. And we get 3 pi over 2. Okay, so we plug everything in. We get S equals R, which is 20, times 3 pi over 2. And we plug that in the calculator, and we get that arc length. That arc length S is approximately 94.25, and this was in centimeters. Okay, so kind of coming back to some important angles. We already did a couple of them in degrees, so let's mention a couple important angles in radians, ones that we should just know what they look like automatically without having to convert between the two. So 1/4 of a rotation. So 1/4 of a rotation would just be a right angle. So a right angle in radians is going to be pi over 2 radians. So the next one, 1/2 of a rotation. 1/2 of a rotation is a straight angle, and in radians, a straight angle is pi. For 3/4 of a rotation, we actually just did that one in the previous example. 3/4 of a rotation is going to look like that. That equals 3 pi over 2. And for the last one, one rotation, so one full rotation, all the way 360 degrees around equals 2 pi radians. Okay, so let's do some examples where we're drawing angles in standard position here. So standard position, once again, we have to remember that the vertex is at the origin and the initial ray is the positive x-axis. So if we want to draw the angle pi over 4 in standard position, we should get comfortable knowing the radians without having to convert to degrees. For now, it's okay to convert to degrees. So pi over 4, I'll try to do them both ways. Pi over 4 is equal to, if you converted it to degrees, it's equal to 45 degrees. So if we were to graph this, 45 degrees would be like this. Change the color so it didn't get too red with all that color. So that would be our angle, 45 degrees, which I'll just label it theta actually. So if you were doing this with radians and you didn't want to convert it to degrees, what I would have said is that pi over 4 equals 1/4 of pi. We know that pi is a straight angle, so 1/4 of a straight angle would put us where we drew it. Okay, so for the next one, we have theta equals 5 pi over 4. Once again, we can actually convert this to degrees for now if it really helps us. So converting this to degrees, we would end up getting 225 degrees. 225 degrees, we would know that it's between 180 and 270, which means it has to be in this quadrant right here, in the third quadrant. So that would be our angle theta. So if I were doing this, the way that I would actually do this is I would say 5 pi over 4. That equals 1 full rotation of pi plus 1/4 of a rotation of pi. So it's a straight angle plus 1/4 of a straight angle, which would put us right where we drew it. Next one for -7 pi over 4. So once again, we could convert that to degrees. We would end up getting -315 degrees. So we have to keep in mind that this is going to be clockwise because it's a negative angle. So initial ray still at the positive x-axis. So if it's -315, that's 45 degrees away from a straight angle. That's going to put us right here because it was clockwise and it was 45 degrees away from completing a straight angle. So that would be theta. Okay, and then for D, for the next one, we have theta equals pi over 8. So for pi over 8, if we converted that to degrees, that would be 22.5 degrees, which we know is between 0 and 90. So it would have to be a pretty small angle here in this first quadrant. So maybe something like that. So what you could say is that it's going to be half of pi over 4. So half of pi over 4. So you know it's going to be a pretty small angle in the first quadrant. Next one, 3 pi over 4. 3 pi over 4 in degrees would be 135 degrees. So that's going to be in the second quadrant because it's between 90 and 180. So it's going to be about right here. And once again, if I were doing this, I would say that 3/4 or 3 pi over 4, that equals 1/4 less than pi, 1/4 pi less than pi. So that would put us 45 degrees less than a straight angle, so quadrant 2. Okay, last one here for F, we have -4 pi. So -4 pi, if we converted that to degrees, that would actually equal -720 pi. And this would be 2 full rotations in the clockwise direction because it's negative. So we go around once for 2 pi, and then we go around again for -4 pi. So that would be our theta. So we ended up going around twice that time. Okay, so you may notice that this actually equals the same as 0 degrees or 0 radians, and it also equals the same as -2 pi radians. It also equals the same as 2 pi radians, 4 pi radians, 6 pi radians, and so on. The initial ray and terminal ray are at the same spot, but the rotation is different. So that actually brings us to the next thing, which is coterminal angles. So coterminal angles are going to be angles with the same initial and terminal ray, but they have different rotations. So all we have to do in order to find a coterminal angle is we add or subtract an integer multiple of 360 degrees or 2 pi radians. So if we do that, if let's say we're in degrees and we're adding or subtracting 360 degrees over and over again, that's going to just be one more rotation around, and the terminal ray is going to be directly back on top of itself. So the actual definition here for a coterminal angle, we can have theta plus or minus 2n pi. So n is an integer being like -3, -2, -1, 0, 1, 2, 3, and so on. So we can have theta plus or minus 2n pi, or theta plus or minus 360 degrees times n. That just means that we're adding or subtracting integer multiples of a full rotation. Okay, so let's do a couple examples here. So let's just find several coterminal angles for the following angles. So it doesn't say what kind, it's not specifying. There's technically an infinite amount of coterminal angles because we can keep on adding or subtracting one full rotation. So if we have 45 degrees, we can add 360 degrees to it. That would give us 405 degrees. So that's one coterminal angle. And then we can add 2 times 360 degrees, which is just continuously adding 360 degrees, which would give us 765. And if we want to, I'll do one more for adding. We can add 3 times 360 degrees, which would just be adding another one, which would be 1,125 degrees. And you can see that we can just keep on going. So let's subtract some. Let's do 45 degrees minus 360 degrees. So we subtract those, we get negative 315 degrees. Subtract 2 of them. That would end up giving us negative 675. And let's just do one more. We would end up getting negative 1,035 degrees. And then once again, we could keep on going if we wanted. So all of these angles are actually going to look exactly, the terminal ray is going to look exactly the same. They're all going to look just like this, except the rotation is going to be different. So 45 degrees, we know looks like this. And if we went around in the counterclockwise direction, negative 315 degrees, it would put us in the same spot. So those are all examples of just terminal or coterminal angles. Okay, next for negative 120, I'll just do a couple of these ones. I'll pause it and fill it out. Okay, so a couple of coterminal angles, I added and subtracted 360 degrees and then 360 degrees again. So 240 degrees, 600, negative 480, and negative 840 degrees are all coterminal angles. The terminal ray is going to be in the same position, but the rotation is going to be different. Okay, let's do a couple with radians this time. So I'll go through and actually write out this one, and then I'll pause the second one and fill it out. So we have 5 pi over 6. So for 5 pi over 6, let's take a look at what it would look like when we graphed it. So 5 pi over 6, so in my head what I'm thinking is that this is actually 1/6 pi less than a full rotation of pi. So it's going to be in quadrant 2, where this is our rotation, 5 pi over 6. Okay, so coming up with some coterminal angles. Once again, I didn't specify what kind. So we can add or subtract integer multiples of 2 pi because we're in radians, so we're using 2 pi. So we would actually have to get common denominators. So it'd be 5 pi over 6 plus 12 pi over 6, which would be 17 pi over 6. Okay, so we can actually do that again. We can do 5 pi over 6 plus 2 times 2 pi. So that would be 5 pi over 6 plus 4 pi. Getting common denominators, that would be 29 pi over 6. And then we can keep on going. And let's just subtract a couple real quick. 5 pi over 6 minus 2 pi. Getting common denominators, that would be negative 7 pi over 6. And let's just add another one, or subtract another one. So minus 2 times 2 pi. That would give us negative 19 pi over 6. And then we can keep on going. So obviously when you're doing these with radians, you have to be comfortable with adding and subtracting fractions. So if you need to review that, definitely review that. So all of these are going to have the same terminal ray with a different rotation. So next for pi over 6, I'll pause it and just fill it out. Okay, so here are several coterminal angles for pi over 6. 13 pi over 6, 25 pi over 6, negative 11 pi over 6, and negative 23 pi over 6. Okay, so for the last couple examples here, this idea is going to come back into play in the next couple sections, so I figured I'd get it out of the way now. So let's find a coterminal angle between 0 degrees and 360 degrees, or 0 and 2 pi radians for each angle. Okay, so between 0 and 360, so I'm going to actually call these coterminal angles. I'm going to denote those with the letter alpha. So for 540 degrees, if we graphed it, it would actually look like a straight angle, except it would end up going around 1.5 times. So this is 540 degrees. So we want the angle that looks like this, because that means it's going to be between 0 and 360 degrees. Okay, so that's going to be our alpha. So all this means, in order to find a coterminal between 0 and 360, we have to either add 360 or subtract 360 until we get an angle between 0 and 360. So for 540, clearly we need to subtract 360 degrees. When we subtract them, we get 180 degrees, and that is our coterminal angle, which we can see by how we graphed it. Okay, next one we have negative 150 degrees. So for negative 150 degrees, that would actually be in quadrant 3. It's negative, so it's clockwise rotation. So we're looking for this angle right here, this coterminal angle, because that would represent the positive version of it. So what we have to do to find our coterminal angle from 150 degrees, we want it to be between 0 and 360, so we have to add 360 to make that happen. So we would get 210 degrees, which would be our angle alpha that we just drew. Okay, next for negative pi over 8, so now we're getting into some radians. So negative pi over 8, it's negative, so it's going to be clockwise. So it would look something like this. So what we're looking for is this angle, that coterminal angle, which would give us the positive version. So in order to do that from negative pi over 8, we have to add a full rotation, which means we have to add 2 pi. We would have to get common denominators, which would give us 15 pi over 8. Okay, and then for the next one, we have 5 pi over 2. So 5 pi over 2, it's a little bit more difficult once again for radians, but 5 pi over 2, the way that I would think about this, 5 pi over 2, that's going to equal a full rotation of 2 pi plus pi over 2, because you can think of it as splitting up the fraction as 4 pi over 2 plus 2 pi over 2. So what that means is it's going to look like something like this, where it goes around once and then goes around 1/4 of a time. So this is 5 pi over 2. So we're looking for this angle right here that would make this an angle between 0 and 2 pi. So to do that, you can probably just eyeball it, and it's actually just sitting right here for us if you wrote it down that way, which makes it helpful. But to do this, since it's greater than 2 pi, you have to subtract 2 pi. So you subtract it, you get common denominators. That gives you pi over 2, which once again is what we probably suspected by looking at it. Okay, next for 14 pi over 3. So a couple harder ones this time. 14 pi over 3. So it would be right on the side. This is how I would think about it. I would think about it as 15 pi over 3. I always try to relate things to the positive x-axis or the negative x-axis. 15 pi over 3, the reason why this helps is because this is the same thing as, I'll write it down here, it's the same thing as 5 pi. So 14 pi over 3 equals 15 pi over 3 minus pi over 3. So once again, the reason why this is helpful is because 5 pi over 3 is actually a straight angle. So this would be 5 pi over 3. If we subtract pi over 3 from that, that means it's going to be plopped into quadrant 2. So this actually goes around a couple times. So it goes around 2 pi, 4 pi, and then it gets to right here. So this would be our angle, 14 pi over 3. So we are looking for this angle right here, which would be our alpha. So to do that, we definitely need to subtract because that's a lot greater than 2 pi. So we're going to subtract, you can try subtracting 2 pi right away, but you would see that you'd have to do it again. So I'm just going to do both of them right away. So I'm subtracting 2 full rotations to get it to be between 0 and 2 pi radians. So essentially I'm subtracting 4 pi, which would get us to 2 pi over 3, which seems like it makes sense because 2 pi over 3 is between pi over 2, and pi, meaning it's in the second quadrant. Okay, last one here. We have 780 degrees. So 780 degrees, that is clearly more than one full rotation. It's actually more than 2 rotations. It's going to end up putting us about right here. So this would be 360 one time around, be 720 for the next one, and then it's going to be an extra little bit to get us to the 780 degrees. And we're looking for this angle right here to get us a coterminal angle between 0 and 360 degrees. So since we went more than 2 times around, that means we're going to have to subtract 2 full rotations. So we're going to have to subtract 2 times 360 degrees. So that's going to be 780 degrees minus 720, which is coterminal angle of 60 degrees. Okay, so that is it for this section.